Okay, so today's lecture, we're going to introduce another framework, okay, which is a PCIe accelerator card. And for this platform, it's different from the previous PINC, okay. For PINC, that's for MPSoC, and that's run on the embedded device. And for XRT OpenCL, that's running with a PCIe accelerator cards. And that platform is used in the cloud data center for application acceleration. Okay, there are three topics I'm going to talk about today. Okay, first, I will talk about the Vitis programming execution model. And that tell you the whole system view and how things are function. And I talk about the OpenCL. And then in the last part, I will take the lab 3 host code and go through step by step, let you know the structure of the code. And this lab 3 source code, or especially the host program code, that will be a template. So in the future, if you want to develop your own application accelerations, you can always reference this code, and based on this code, you make a modification. So that's why you need to fully understand the source code of Lab 3, yeah, so that you can adapt it to your own applications. Okay, basically, this is the Vitis computing execution models. Okay, so so when you have a application, originally is run on the host CPU, okay, and then you want to move your kernel function to the other parts, to the FPGA. So what you will do is first the host program will prepare the data, okay, put into the host memory. Okay, in here there are several memory. You have to distinguish host memory and the global. Okay, so the host program first prepare data and put into the host memory, and then you move the data. Okay, you move the data to the global memory because the is not exactly right. Yeah, and the Vitis programming model. In reality, the PCIe accelerator card can always operate on data directly from the host memory. Okay, but in the Vitis or the OpenCL programming model, so they operate on the local memory, which is the global memory here. So you move the data to global memory, and then this accelerator function and will get the data from global memory. Okay, and in here there are two things you have to pay attention. Okay, first, to move the data from host memory to global memory, you use some sort of DMA. Okay. Data from global memory, you use XI master. Okay, if you recall when we talk about embedded system, for embedded system, you have a PS and PL part. Okay, and for PINC Z2 board, you only have a one memory, which is hooked on the PS side. Okay, how is it different from that? Yeah, and in here you have a host program, host memory and local global memory. Yeah, so let's give you a reflect on the PINC embedded. So actually, the PL, you use the master cycle. Okay, you use the XI master to get the data from here. So this memory serve as a host memory for the PS program, also serve as a global memory for the peer, for the kernel function. And in here, the peer using XI master access the DDR memory here. Okay. So in Vitis programming that you use a DMA to move to the global memory, and here you use the global memory. Okay. So for certain embedded device, you do have a local DDR memory on the peer side. Okay. So for certain like a ZCU104, okay, the board has a local DDR memory, the peer side. So that will operate exactly like this model. Okay. From global memory, and then actually dial back to the global memory again. And then the host program uses a DMA to transfer the data from global memory to host memory. Okay, and then the host program doing the post processing and check the result data. Okay, I hope it's clear that you understand the whole programming and execution model. So when you take the code, OpenCL code later, then you will know that you need to allocate the memory on the host memory, and then you need to memory from global memory, and then you will say I want to do the DMA transfer. Okay, and then you set up the parameter on the kernel function and execute the kernel function. Okay, and then when it's done, and then you do the data movement from the global memory to the host memory. Yeah, so when you study the OpenCL code, you will see they perform all those steps. Okay, so I'd like to also talk a little bit more about the data transfer between the host memory and the global memory, because this computing model is a standard low store type of computing model. So it's not efficient. As you can see, there are many data movement. Okay, first the host program prepare data right to this memory, and then you write to from host memory to global memory, and then from global memory load into the kernel function, maybe the local block RAM. You see how many data transfer? 1, 2, 3. Okay, so you have a 3 data movement to get the kernel to execute. Okay, so it's not very efficient. So in here, I would like to touch a little bit about is there other way to do it more efficient. So when you design in the future, when you design your own application accelerator, you probably need to consider using the new method. Okay. So there are several ways. Okay. So besides, so that's the Vitis way. Okay, I already introduced. And second method is how about we use the AXI master, the kernel function, using AXI master to access host memory directly. That would be more efficient, right? If there's DDR. Since this kernel function is a PCIe device, so the kernel function can use the running as a PCIe master cycle to get the data directly to its kernel function memory, like a block RAM, and then you can operate right away. Okay, so in the future, you probably need to exercise that. I remember in the lab A, one of the lab will try to doing this exercise. Yeah. So you reduce from 3 memory access to 1 memory access. So you save the power and you save the latency, right? So it's perfectly durable. Yeah. Okay. And the third one, if sometimes the host program and the kernel function, they simply like to transfer some parameters, the data. Okay. And you can do in the streaming host to kernel streaming. Okay. For this one, okay, you can see the data transfer is very efficient. However, there is another overhead called control synchronization. Okay, you need to have a concept that to do a data transfer, the whole process, not just data transfer. And there is a control mechanism. For example, when the device can do the transfer, right? So you need some kind of a control command that what I call control synchronization, and that's the overhead. Okay, for doing, I'm telling you to do the data transfer. This action takes a latency. Okay, so that means the actual data transfer gets delayed, right? Unless you use some techniques like prefetch, right? Before the data actually needed, you ask them to transfer earlier. Okay, and for this kind of the prefetch, those mechanism is it's complicated and you can make mistake easy. Yeah. Okay, although it's good, but not really good. Yeah. Okay, because the control synchronization takes up some latency. So how about we are doing this way that the kernel, instead of a control driven, we use data driven. If the kernel, we change the interface, that's a memory interface, XI memory or PCIe. Let's change to string. Okay, string you can think is a FIFO. So what happened? The kernel can start running when the data are available. Okay, so this is so-called data-driven scheme. Yeah. So the kernel is always running. So there is no control synchronization. I don't need to use another channel to tell you to stop because you separate the control channel. Okay, so you have a control channel and data channel. What I'm talking about is a very advanced system design concept. Okay, so if the whole mechanism for doing the communicate with the kernel function has a control channel and data channel. So if there are two independent channels, so they involve the synchronization between them. Okay, yeah, synchronization takes latency and overhead. Okay, it's complicated. Yeah, we really want to eliminate that. So how about we put the control inside one channel, just one channel. And inside, the control is regarded as a data. And then you have a payload, like Ethernet, right? Yeah, like Ethernet, you have a header tell you all about this packet. And then you have a payload. Okay, and Ethernet is just a single string, right? So how about we use this model? Okay. So if we use this model, then this kernel function need to be designed in a way is data driven. Okay. So whenever this train has a data, the kernel function can up and running. You always monitor this FIFO channel. If this FIFO has a data, my kernel start running. Yeah. So you have to design kernel in this way. Yeah. So that's another way using the string mechanism to transfer data. Yeah. For example, so there are many good things to doing this way. For example, another way is let's say that you have a PCIe accelerator card and you have a Ethernet. Okay. And right now the acceleration is working on the request from Ethernet. Okay, you wonder if there's a remote host. I want to use the acceleration here. Or I want to use the storage here. Of course, like a network attached storage. Okay, for this kind of application, what would you do? First, you send a request over, and then the driver, the host, the CPU driver, okay, take the packet and save it in the local memory. And then you will trigger this kernel function, and then pass the data over, right? So it's better doing this way. You have the Ethernet, that's the PCIe and the PCIe. The network packet directly pass through without the driver or host CPU involved. Would that be good? Yeah, very efficient. Yeah. And today's inside the chipset, there is a PCIe switch. Today's chipsets, okay. Before, like over 10 years ago, Intel chipset doesn't support that, but later they have a chipset support PCIe peer-to-peer transfer, so that they can forward a PCIe packet directly to another PCIe bus. Yeah, so you can do things like that. Yeah. Okay, so hopefully you can grasp some idea. Okay, and this programming model is very flexible and very easy to design. However, you can see a lot of inefficiency involved the whole data transfer path. Okay. Okay, let's talk about the OpenCL programming model. Okay, so we have a XRT on below, and then you have the OS driver, and then you have APGA. Okay, the XRT support the OpenCL. Okay, XRT expose certain API for the program written in OpenCL to access your kernel function, and they also support XRT native API. Okay, XRT native C++ API. So when you check out some open source code, you will find out the host program is written in XRT native API instead of the OpenCL. However, those two has the similar concept. Okay, and you can refer to the detail if when you get the open source code, which is written in XRT native API, you can reference this document. Yeah. But basically, the idea is same as OpenCL. Okay, next let's talk about OpenCL model. There are like full area that I'm talking about. Okay, first step. Okay, when you start an OpenCL coding, first you need to identify the platform. Okay, you use the code. You see the get the platform information. So you need to know what the platform covers. So for a platform, basically involve a host and the OpenCL devices. Okay. Okay. So inside each, or you can think of that's an FPGA chip. Okay. So the OpenCL device is PCIe card and an FPGA chip. Okay. And inside this FPGA chip, you could have a multiple compute unit. Okay. And you can think that the compute unit is a so-called text level parallelism. Okay. And inside the compute unit, you have a multiple PE. And PE, you can think of that's like a data parallelism. Okay. So it's an execution model. Okay. When you execute something, there are certain things involved. First, to execute something, that involves two parts. One is the host program. One is the kernel program. Okay, the host program run on the host, the host exe executable file. And for the kernel program, actually is a bit string, which used to program the FPGA device. And in the left tree, you will see this kernel corresponding to XCL bin file. Okay, so that's a whole execution that involve these two. Okay, and go inside that to look at the host program. So that first you have to set up a context. Okay, a context is a collateral of the following objects. Okay, and you use the API to manipulate those objects, including the device, the FPGA chip you use, and the kernel function inside the FPGA chip. And also the program object. Program object you can think of that's a bit string. Or the bit string. And you have the memory object. Okay. So when you start running something, you have to set up the context. And the context include those actually also include the command queue. Okay. And for the command, there are it is used to coordinate the execution of the kernel. Include the kernel execution command. Basically, to program the parameter arguments and then trigger the kernel function. Okay, like in the pink, that like a start, right? You basically trigger the kernel execution. And you have a memory command to move the data around. And you have the synchronization command. Okay, synchronization, let's try to map into the pink. You all familiar with pink, right? So trigger this one, the kernel execution command that like a start signal. Okay, so when the kernel execute, you assert the down signal. Okay, so that's a physical signal on the in the FPGA chip. But when it's across PCIe, so basically you send a message or send a packet, PCIe packet over. Okay, so there's a command queue contain those three things. Okay, so you have to know these things so you can understand the OpenCL code. Okay, let's talk about the memory model. Oh, okay. So we were talking about the global memory. Okay. So the global memory is used to communicate with the or transfer between the host memory. Okay, and then there is also a constant memory. That means that the memory won't change during the runtime. Okay, and inside the compute device, there are different memory hierarchy. Oh. So the closer to the execution, the processing element, the faster of the memory. So you can think of in the processor. Okay, and inside the compute device, you have a so-called work group. Work group is a collection of that's a CU, compute unit. You can think of the compute unit like the cluster of CPU core. Okay, so you can think of this is a CPU. Okay, and inside the CPU, like you have for example, you have a 32 core CPU, and for Intel that because 32 core sharing a cache, there will be too much traffic and the distance will be too far. So they partition the CPU core and also partition the cache memory hierarchy. So for each CPU core, you can think of the PE is a CPU core, and it access the private memory. The private memory you can think is corresponding to a level 1 cache, level 1 instruction or data cache. Okay, and for a cluster, for example, Intel CPU may have a 4 or 8 core pointing to a cluster. For the cluster, this part you can think of it as level 2 cache. Okay, so for 32 core CPU and 8 core in a cluster, then you will have a flow cluster. Okay, each has a private level 2 cache. And then you have this part like a level 3 cache. Okay, so it's different from CPU. For CPU, that guarantee all the memory is globally coherent. So whenever there is an update in the cache, even though L1 cache, this update will broadcast to other place because in the CPU there's only one globally visible address space. So inside the CPU, it has very sophisticated cache snooping design. But for the FPGA, otherwise takes up too much gate counts. Actually, in CPU, the cache coherence, the tag memory, take out a lot of die size. Okay, but for FPGA, it doesn't do any of the those memory snooping. Okay, so that means every device, the PE can only access its private memory. Okay, and your kernel function has to explicitly to move data around. Okay, it's not like a CPU cache. When you access it's a cache miss, then automatic to fill the cache, update the cache. And also when you write to a cache, you will make sure all the update will broadcast to other cache so that they are globally coherent. Okay, but in FPGA, you partition those data, then you have explicitly to move data around, and your program code has to make sure that if you modify a part of data here, and you want to another kernel function or PE process the same data, you have to explicitly transfer data to its private memory. Okay. Okay, so it's a memory hierarchy just like a CPU, but it doesn't have a cache coherence mechanism. Yeah. in this way. So this is the memory model here. Okay, this is an example of the OpenCL diagram. Basically, it tells that's OpenCL defined as a hierarchy of a class object. That is a relationship among those objects. So you can know for this one, okay, for a program that the program can load into multiple kernel. Look at the symbol here. That means one program can be loaded into the multiple kernel. And a device could have a multiple program or multiple kernels. And the program can also pull into multiple FPGA device. Okay. So for a context, as we talk about, you have the device, you have the kernel and program, and also the command queue and memory object associated. And it tells the relationship between them. Yeah. And also the class attribute inheritance relationship. Okay. So this picture simply gives you a better idea how those context objects related. Okay, let's come to the Xilinx runtime XRT. Okay, so let's look at the whole framework of XRT in these pictures. And the Xilinx Vitis XRT, they support two kinds of device. One is the PCIe device. Okay, they also support the NPSoC. Okay, you can think of this is the FPGA. So it supports the PCIe attached device. It also could support the NPSoC, the kernel Express. Okay, so for this one, it's the NPSoC. However, the way it connects to the host is through is a PCIe interface. Not like this one is an NPSoC, but the kernel, okay, in NPSoC, the kernel running on the PS side, and this part running on the host CPU. Okay, so PS side, that means it run on the ARM processor. And this one most likely running an x86 processor. Okay, and then on this part, they are pretty much the same sharing among the either ARM processor embedded system or the x86 host servers. Yeah. Okay. So in terms of the function, okay, the XRT function, you can I also put the pink framework here. Okay, you can find the correspondence between them. So XRT function include the image download. So same with the pink. Okay, you handle the image download using this driver. Okay, and use you also have the memory management functions. Okay, for this one, it's like the pink XL link. Okay, like this one. The driver here, doing all the memory management. Yeah, and it has for the execution management. It can queue the task queue management, and it support the out of order scheduling, and you can also polling the task completion status. Yeah, and you can also do the hardware schedule. Okay, so this one with the pink corresponding to the MMIO. Remember when we write the pink that you as a user host program, you have to manually control the start and monitor the down status. Okay, for those customized kernel function, you have to manipulate them, yeah, directly, yeah. And for that, for the XRT, you don't really to look at the kernel function the configuration register signals. Okay, you through the API, using the API, they provide the in-queue task or those API to manipulate the kernel executions. So this one, so for the execution management, okay, map to the pink MIO. Okay, and in here, there's one thing very important I like to point out is it can have a microblade. It's a very tiny, small microprocessor that you can put on the FPGA. Okay, so let's look at this. Let me draw why you bother. Why do you need to bother to use a microblade processor inside the FPGA to do the fine control of the scheduling? Okay, let me briefly talk about this concept. This concept is also very important to do the high performance design. Okay, and in current model, okay, you have a host program, and you have the FPGA, and FPGA you have a kernel function. And currently with PCIe attached card, use PCIe, and PCIe there's a PCIe IP. Okay, and they insert certain module here. Okay, so you have a host program to do the scheduling. Okay, let's say that you have a multiple kernel. There are many kernel, and you running different tasks. Assume, let's say, out of order operation. Okay, so that means each kernel function, you have a multiple kernel function running at the same time, and all the running status you have to report back to your scheduler. There's a scheduler. Okay, how do you do the schedule? You send the PCIe packet. Okay, and you want to trigger the start, you also send the PCIe transaction. So it starts. And when, okay, for example, if you do the data buffer movement, your data try to move here. When the data move using a DMA, you using a DMA move data over. Okay, when DMA finish, then you have kill the schedule that the data is transferred down. And the kernel function, when you trigger, when it's down, then you send the PCIe packet, and then when you receive, it's down. Okay, so what's involved here? Not just the hardware path. The hardware, of course, takes a latency, especially PCIe. PCIe is a serial bus, so there will a serial to parallel to serial. All those transaction conversion. And but what really the overhead is the OS driver, the drivers. You know, when the packet comes in, you trap into the kernel. You know, the kernel context switch takes a long time. Okay. So for these things, all the communication take a really long latency for synchronization overhead. Okay, even though your CPU run very fast, 3-4 gigahertz, but those latency is not the CPU speed can accommodate. Yeah. So what you really want is put the scheduler inside the FPGA, right? Yeah. So right now you have a FPGA and you have a MCU. The MCU is inside the FPGA. So you have a kernel function. Okay, and kernel function using a very direct wire to the MCU through the interrupt or anything, or even the MCU is written in a code using polling. Sometimes polling is faster because you use the interrupt, then you trap and then you have to pull which one give you the interrupt, right? Yeah. Imagine there are multiple interrupt sources. So when an interrupt happen, the interrupt handler have to pull in each device and see which one give you the interrupt, right? So sometimes the code just doing the polling. You're polling each device to get its status. Sometimes it run faster with polling mode. If this MCU is dedicated for that function. Okay, so this one gives you much efficient scheduling with very short latency. Yeah, so that things can run very efficient. Yeah, so that's why I like to elaborate more about this approach. Yeah. I believe they have a open source code for doing the hardware scheduler. Yeah. Okay, so basically that's a XRT runtime. Yeah. Okay, the development flow will be like this. So for the application program, you split into two parts. One is running at the host, one is running at the kernel. And running with the host, you use the GCC compiler. And then you compile into the host executable file. And for the kernel, you go to the Vitis, the V++ compiler. Okay. So your program code, the kernel function could be in the AAHLS written in C or C++, or part of the kernel can be the RTL code. Okay. For the AAHLS, you use the V++ compiler. Okay, this V++ compiler is a standalone. And this one, you can also use Vitis HLS, that's kind of GUI. Okay, so when you're doing initial development, you're doing a lot of debugging and performance tuning. So it's better that you develop the HLS in the Vitis HLS. So it provides a lot of analyzer too, and then you can evaluate the resource, performance, everything. So when it's done, that you can convert to this path. Okay, with the proper pragma and the source code developed, then you go through this flow. Okay, the RTL code just a standard process. You simply package it into the .xo file. So you have a multiple object or multiple kernel function, then you can integrate them and by linking them together becomes a V++. And then it becomes a XCL bin file. Okay. So for this path, okay, this path is totally same as a software development process. That means you can use the Makefile, okay, to automate everything. Yeah, to compose the whole FPGA system. Just you like the complete the same as the software development process. Yeah. Okay, so when you develop the software and then you simply execute them. But right now the executable has two components. One is the host program, one is your kernel function. Yeah. So exactly the same. Okay, it's a software development. And so when it's ready, then you can run the hardware mode. You simply execute your host program with this one. Okay. Or if you are doing the software emulation or hardware emulation, okay, software or hardware emulation. So this one you got to use this using this utility, and this utility will provide the profiling and the optimization and debugging features. Okay, so you go through iterate between the software emulation and hardware emulation. You use the software emulation to make sure it's function correct. You use the hardware emulation to improve or evaluate its kernel function performance. Okay. The hardware emulation does not really reflect the actual system performance. Okay, imagine you are doing the hardware emulation, and this kernel function, you actually run the Verilog simulation. So it is cycle accurate. Every cycle will exactly match the real hardware. However, another thing is different from the running in the actual system. For example, the kernel function access the memory. Okay, but remember, in the whole system, there are other processes also access the memory. So the latency of the memory is not accurate. And the memory controller is not a real memory controller either. Okay, and then the PCIe traffic and PCIe latency, the PCIe device behavior is not the real one. They are behavior models. Okay, however, it's good to evaluate your kernel function performance, and it's also good for evaluate the scheduling. Okay, remember we are doing the out of order operation, right? So when you are doing something out of order, things can become very complicated. Because remember that in our last lecture that we're talking about race condition. Things not in sequence, they all happen random orders. Then the synchronization and certain event, they may have a race condition in your code. And so you can use the hardware emulation. Definitely, you cannot simulate that in software emulation. But to some degree, you can emulate this, or maybe find out the race condition through the hardware emulation. But it's not the coverage is not enough. So you have to run the actual system hardware to observe the real system behavior. Yeah, and also you need to run very long time. You have to run long time, and to doing the profile to find out the real worst latency. Or yeah, you have to run very long time, and especially you have to put pressure on the system. At the same time, you have to turn on the profiling. Okay, even though running on the actual system, remember when you're doing the actual FPGA emulation, you want to turn on the profiling. The profiling at the overhead, okay, slow down the whole system operation. However, give you very timing waveform, give you a lot of insight about the system operations. Yeah. And also a good design I will recommend if you are really doing the product development, I will recommend that you have to do the burn-in. Okay, in the burn-in process, that you have to put pressure on the system, and you also have to turn on the profile. Okay, the profile gives you the insight of the timing data, and in the timing data, you probably need to draw a histogram. For example, during this system running, you probably drawing a histogram. The histogram, for example, that's the latency. Okay, that's the frequency. Okay, and then you draw curve like this. Okay, so and depending on your system requirement, I say that I want to have a system running with maybe two. Normally we will say 2.9. Okay, 2.9 means 99.99. Oh, okay, yeah. Oh, 4.9. Actually, that's 4.9. Okay, so that means you got only 0.001%. Okay, 0.1% that were greater than this latency. Okay, if that's your system spec. Okay, I say my system spec give you 99.99 latency within certain latency. Okay, imagine the more night that the design is more strict and you need to put more resource buffering or all those things. Yeah, but how can you give a really informative number? Then you have to run an actual system and connect that. Yeah. Okay. Yeah. Okay. And next, we will talk about lab 3. Yeah. Basically, I will take you go through the code. Okay. For lab 3, actually, that's a very simple lab. It really doesn't do any meaningful calculation. Okay. So what's demonstrated in this lab is how do you schedule the kernel. In this lab, we have 5 kernel running at the same time. Okay. And we have a data buffer. So it gives you a framework. It's a very typical application. Multiple kernel and multiple buffer, and then how you do the synchronization between them. So that's why I said that the lab 3 source code is good. You can use that for your future application development. But you do need to really understand the internal mechanisms, yeah, so that you can adapt this code to your purpose. So in this lab, we have 5 kernel functions. Okay, and then we have multiple buffers. In particularly, we have these 3 buffer only local to the global memory. And this buffer, the 3 data in and 1 result buffer, will have a copy in host memory. These 3 buffers. Okay, and this example also demonstrates an order operation. Yeah. And inside this kernel, it's a very simple operation, just doing addition or multiplication. Yeah. Okay, first let's look at the kernel program. Okay. And there are a few things you need to pay attention to the kernel function. Okay. This part, the body of the kernel function is really doesn't matter. Okay, you can do whatever. Okay, what is the demonstrate is look at the pragma here. Yeah. First, you always need to put this one. If that's the kernel function that gonna to expose to host program control, then you need this put this XI light. Okay, this one provide proper control signal like AP start or AP down. If you develop a kernel function that doesn't need to communicate with host or it's not controlled by the host, then you don't need this. Okay. And for the argument, that there are in this example there are 2 kinds of argument. One is a data payload, okay, and you use a XI master to access data from global memory. For example, the data from the global memory, and you use the XI master to access from the global memory. So to do that, you need to have a base address. So that's why you need to have an XI light for the argument V. That's an array. Okay. So the XI master almost always come with a corresponding XI light to specify its base address. Okay. And this argument arg, okay, is directly that's it's a configuration space. That's just a parameter that the host program directly program. Yeah. So the host program the kernel argument using the XI light. Okay. So this one is also in the pink lab 2. Yeah. And remember that there's one thing here. In the pink lab 2, for each argument, you look at the HWH file to find out the argument offset, right? And then you specifically specify the offset to program that argument. But in in the XRT, there is no address, no offset idea. Okay, so how do you specify individual argument? You look at the argument sequence in the argument list here. Okay, you use the argument 0 for first one. Maybe next example, yeah, here. Okay, in this KPB, you have a 3 array. This one has a 3 memory buffer here. Okay, so they are pointer to the memory buffers. And then the argument is written ABR. That's the argument order. So if you want to specify the base address of this buffer for A, then you use argument 1, argument 2. There's a sequence number. Okay, I think it probably start from 0, 0, 1, 2. Yeah. Okay, you don't use like a pink, you use offset address. There's no offset address. You have an index. Okay. Okay, so that's all you need to know how to write the kernel function. Yeah. That's a difference from the pink. Okay. Okay, the main part is on the host program. Okay. Okay, to execute them simply like this one. Okay. So for the OpenCL, the host program has these 3 major steps. Okay, first you need to set up the hardware, and then you execute the kernel, and then doing the post processing. Yeah, and that's the things that you need to do in each step. And setting up the hardware, yeah, you have to identify the platform, create a context. Okay, and then program the FPGA, that's the program. Yeah, and then create kernel objects. Yeah, so you have some idea from the previous slide. Yeah, so let's look at the actual API code. Yeah, so that's the steps. Okay, let's look at here. So in this code, first you have a get the platform in here. Okay, remember in this system, you want to run it. Okay, remember the XCL bin file is compiled with a specific the vendor, right? Which is the Xilinx. And the XBin file also compiled with a specific device or the FPGA board. Okay, so when you supply this XBin and execute them, you have to make sure the XCL bin is loaded into the correct device. That's the purpose of discovering the platform and device. Okay, so when you discover the platform, Okay, those are the API. And for detail, you can look at the textbook. It has a link to the detailed documentation. Yeah. But basic idea is first you get a list of platform installed in the system. And from the list, because in a server, you may have a GPU, NVIDIA GPU, you may have a Intel FPGA, you may have a Xilinx FPGA. Okay, so look at the whole system, and then since it's an OpenCL, so every device, if that's an OpenCL device, it's going to expose a protocol, a handshake, and then using a unified way to query the status of this device. So that's a standard, so that you can query each device on the system, and then you want to identify the platform vendor, which is Xilinx. Okay, in here you find out this car is a Xilinx car. The next step, you want to find out the device is the correct device. In this example, since it's in the initially this lab is running in the data center using the U200. So this you may change to U50 in your lab. Okay, again, right now you try to get the older device with the platform ID, with Xilinx. You try to get the Xilinx device in the system. And you identify this device, target device, among all the devices. Make sure the device you identify is this device. And eventually you got the target device ID. Okay, right now you locate the right device, which you can load the XCL bin file. Okay, and then we will create a context. Remember, context include the device, the program, the kernel, and memory object. So right now we're going to set up the context. First step, you create a context using this OpenCL code. Okay, and with this target device ID. And then you create a command queue. Okay, using the CL create command queue. You indicate whether you run the command queue in order or out of order. Okay, you put a 0, that means it's in order. Okay, for the command queue, that there are 3 types of command queue. Yeah, common execution command, memory command, and the synchronization command. Okay, so first you create a command queue, and then you can insert the command. Okay, and using there are 3 types of different commands, so you use a different API. Okay, to insert different type of command. We will see it later. Okay, I just and then you create command queue that, yeah, if you run it out of order, you can use this macro definition here. Okay, once you create a command queue, and the next step is you create a program and the kernel. Okay. And first, for the program, you from the disk, you load the XCL bin file into the host memory. Okay, and then you create a program. Okay, and then given the XCL bin file already loaded into the system memory. Okay, so I believe what it does is load the XCL bin file into the FPGA device. And then you create individual kernel. Right now you have a 5 kernel, so you create the kernel. So this gives you the kernel object. And then later on, you can operate on each kernel. Yeah. So right now, you already set up the program, also the kernel, and then we want to execute the kernel. To execute the kernel, first involve the data movement. Okay. You have to set up all the buffers, and then you have to program the argument, and then you're doing the data transfer. Okay. So you have to do the set up the buffer first because the buffer address got to set up into the kernel argument. Yeah. So that's why you have to remember those sequence. You have to follow the sequence. Yeah. Yeah. Without the buffer data buffer allocate first, then you cannot program the argument. Yeah. So only if you create the argument, then you can do the data transfer. Yeah. And when data move to global memory, then, right? Yeah. If the data is not moved to the global memory, you cannot execute kernel because the kernel only execute data from the global memory. Yeah. So those steps, yeah, it's by reason, yeah, you know that has to be this sequence. Yeah. When it's done, then you synchronize the event. Yeah. Okay, so here, allocate the buffer. First, you allocate in the host buffer, and then you allocate in global memory. So for the buffer in host memory, you always have a shadow global memory buffer in the FPGA global memory. Yeah. In addition, you also create some local buffers. Okay. And first step is allocate buffer in host memory. And first, you allocate the host memory buffer. Make sure it's 4K aligned. So you don't use mallocate. Yeah, this one because the mallocate doesn't guarantee not even 4 byte align, not even integer align. Yeah. So you have to use this memory allocation. Yeah, that guarantee is a 4K align. Okay, 4K means it's a page. That's the page size. Yeah. Okay. So you create each buffer, data in 1, 2, 3, and also the result buffer. Yeah. And then next step, you create the global memory buffer. Okay, so there are total how many of them? Maybe 7 of them. Yeah, you create 7 buffers. Yeah. And the buffer has a different attribute. For the data in 2, data in 3, that you specify, first you specify the read-write attribute. Okay, for data in, it's both read and write. But for buffer data in 2, that's a read only because kernel function only read it. Yeah. And these 3 buffers is you use the host pointers because those buffers coming from host memory. And the other buffers created locally. And for the result buffer, you also share with the host. Yeah. Okay, you specify the attribute, real attribute, and you specify whether the buffer is scheduled from the host memory. Yeah, using the host pointer. Okay, setting the kernel argument. As I said that you use the index here to specify which argument to program. And the index is specified order of the argument list. Okay, so for the KA, the pointer A array, so that's the first argument. So you specify as index 0. The next argument is 1. Yeah. Okay, so it's clear. Huh? And the next step, and then you transfer the data from host memory to global memory. So there are 3 buffers you need to transfer. Data 1, 2, 3. So you use the CL-NTHU migrate memory object using this OpenCL. This one is a little bit different from before. It used CL-NTHU write buffer and NTHU read buffer. Okay, so before these two, they're actually doing the data transfer, and you use the NTHU using this API. You actually register a command, and that command is not executed when the dependency event fulfilled. Yeah, so that allows you to do things ahead of time. Yeah, I mean, set out the command ahead of time, and also allows the data transfer to overlap with the kernel execution. Okay, so you use NTHU migrate object. Yeah. So in here, by using this API, it gives you an opportunity to overlap the memory object with other unrelated operation. Yeah. And you also respect the dependency on them. Yeah. Okay, and this curve is also important. I like to elaborate more about this one. And this curve, you see here, that's the buffer size, and that's the PCIe throughput. Okay, and the host and the FPGA, the data transfer is of course PCIe bus, and the PCIe bus bandwidth is a critical factor in the whole system design. So you really want a very high utilization on the PCIe bus. Okay, and that utilization is really depend on your buffer size. Every time when you transfer the buffer size, yeah. So why does it matter? Yeah, I probably elaborate more about this. And let me create a new slide here. Okay. First, let's talk about the bandwidth issue. Okay. Let's look at the DDR memory. Okay, in the system DDR memory. Let's talk about the DDR4 give you the 3.2 gigahertz. Okay, and then each memory channel has a 64-bit, which is 8 byte. Okay, this one gives you 25 gigabyte bandwidth for one memory channel. And in FPGA, you may have a full channel of a DDR memory. Okay, so you have got a 100 gigabyte memory bandwidth. Okay, so that means you access the data if it's local, like a host program running, then you have maybe 4-channel, 6-channel memory bandwidth. That's so. Let's talk about PCIe. Let's talk about PCIe Gen 4. Okay, so that gives you 8 gigahertz, and you have let's say you have a 16 NAND. Okay, so this one gives you 16 gigabyte. Okay, so if for every computation, the kernel function compute the data which coming from host memory, that means you have only that much of a bandwidth to use. Compare if I run in the host memory with DDR, that's 100 gigabyte. So this fundamentally already limit the maximum performance you can get. Yeah. So this gives you a sense why PCIe, the throughput is very critical. Yeah. I can take another example that Let's take you have a FPGA. FPGA, you use a DSP. Okay. So in the next lecture, I will talk about FPGA. Okay. So let's say FPGA, you're using a DSP. Okay. For FPGA, easily you have several thousand of a DSP. Okay. Let's say you have a 2,000 DSP inside. Bigger FPGA even more. Okay. For each DSP, let's say A times B plus C perform the MAC operation, and it takes 3 arguments. Okay. Each argument, let's say that's an integer. Let's say just an integer, 32 bytes, 32 bits. Okay. So that gives you 12 bytes, right? And you have a 12 byte and you have a 2K DSP. And let's say the FPGA running at 300 megahertz. Okay, how many bandwidth is this? Wow, 2K. That's already gigabyte, right? Yeah, so 24 gigabyte. Even more, 12 byte and 2K megahertz. Oh, you have times 300, sorry. And times 300. Wow, that's terabyte bandwidth, right? So you will see that the performance bottleneck often is not lies in how many compute elements you have. Okay, bottleneck is really on the memory, how fast the throughput of the memory that you can provide. So always concern about memory bandwidth. Always concern all the data bus is efficient use. Like even though you have a DDR, even though the FPGA access 4-channel memory, you have only 100 gigabyte, and this one you are talking about terabyte of a data throughput unit. Yeah. So one of the key system design issue is how to, since the bandwidth throughput, that's a theoretical throughput, there's nothing you can change because the system is designed this way. But what you can do is increase the utilization. That's the key design object. You try to improve or maximize the bus utilization. Okay, and then let's go back to this curve. Why the buffer size matter? And that's a PCIe throughput. Okay, let's say you have a data buffer here. Remember, to transfer data, you use it to transfer the data to the DDR memory. Okay, so this one you need to initialize. You need to program a DMA controller before it can start doing the data movement, right? Yeah. And for host CPU to do this program across the I/O bus, it takes latency. When the data buffer transfer down, it tells you, and then you can start next one. Let's say that you have, and typically this system takes 30 to 60 milliseconds to do the I/O programming. Yeah. So let's say that to do the program takes that much time. And if the data bus, if the data transfer depends on the data buffer size, you can see the data transfer time on the PCI link, depending on the buffer size, right? Okay, if the programming time is greater than the data buffer size, then you will have the PCIe bus idle. Right? Yeah. So that's the reason why you want to increase the data buffer such that the programming, let's say that you have a bigger data buffer to transfer across PCIe and take that much time, duration. And so that's why when you programming down, then while you are still doing the and then doing the execution, then you can pipeline another programming. But so basically, you want the data buffer size such that the transfer of the data buffer take at least or even longer than the programming time, so that you can fully utilize on the PCIe bus. Yeah, so that's why this curve shows when the buffer size reaches certain limit, then that saturate, this part you saturate the PCIe bus. Yeah. Okay. So that's another example. That's the reason why for one programming, you want to do multiple data transfer. So you can use the enqueue migrate memory object. Yeah. Okay. The next one, that's how you do the how do you program the out of order execution? Use that's into the memory object. That's into the kernel execution. Yeah, and the last three arguments specify that the dependency. Okay, that's a waiting list you depend on, and the event list is specified in the next argument. And when this task complete, you will assert another event that's specified in this argument. Okay, let's take this example. This example is purely in order execution. So you create a command queue with 0 specified here. It says it's in order. So first you enqueue this memory buffer A, buffer B, and then you trigger the full kernel execution using the CL enqueue task. You trigger the kernel execution. And when it's done, and then you specify, okay. Yeah, you specify the to transfer the buffer result buffer back. Yeah. So since that's in order, so there is no dependency here. Okay. But in this example, it shows the out of order execution. That's the dependency graph. Okay. So first you have to transfer buffer A before kernel KA can execute. Yeah. Buffer B transfer first, then start the kernel B. Yeah. And the KX kernel function depends on kernel A and B complete. So that's the following is the way you write your code. Okay. First you create the command queue. It's an out of order. This one says out of order. And then include these two objects. Okay, it doesn't need to depend on anything. But when the data buffer transfer complete, you will assert event 1. Okay, this assert event 2. So for KA to start SQ, there's one dependency, depend on event 1. For kernel B to start SQ, you depend on event 2. For KX kernel to SQ, you have to make sure KA and KB complete. So it depends on 2 events. Okay, so you still have 2 events here. And this one means starting from 3. Okay, so basically wait for event 3 and event 4 complete before it can start. When it starts, it generates event 5. So for K result to execute, then you have to wait for KX complete. Yeah. So you use this the last three arguments to specify is a dependency graph. And the XRT kernel scheduler will follow the dependency to schedule or trigger the kernel function accordingly. Okay, another way is using a barrier. You can put a barrier here. Okay, so barrier here, say wait until all the command queue flush, or the previous event complete. Yeah, then it proceeds. So that's another using barrier. Yeah. Okay, so that's this lab example. Yeah, this lab. So what you pay attention is calculate this kernel function depend on KA and KB. Okay, so wait for two events from the two. There's a KA and that's a KB, KPP. Yeah. Okay, so after complete all the kernel execution, then make sure that you do the cleanup. Okay, otherwise it create because each object takes up the memory and its data structure takes up the memory. So you have to free the memory. Otherwise, when the system continue running, the memory get leaked. Then you may run out of memory. Okay. So at the last, the lab 3, so basically you can run the Vitis analyzer. When you're doing the hardware emulation, it generates a summary report. Okay, and then you can use Vitis analyzer to take a look at all the timelines. In this particular, when you do the out of order execution, then you will see the kernel A and kernel B running concurrently. Yeah. Yeah. So basically, XRT, since it does all the scheduling, so it keeps track each kernel function when it's triggered and when it's done. So he keeps track of all the timestamp for each operation, including the data buffer transfer, the kernel execution. Okay. So when you actually run in the system and you turn on the profiling option, turn on, then it will connect all the timestamps. So later on, you can use a visual tool to display the timeline and doing the analyze. Yeah. So it's very important when you write the sophisticated host program, you do need to detailedly investigate the timeline to make sure it behaves the way you expect. Yeah. So it's very important. Yeah. Okay. So this one is I probably don't address that. Yeah. So that's a very advanced system architecture concept that you can use a very low cost and low power MPSoC to replace a very high-end server. And I won't address that. Okay, so let's take a break till 11. Okay, take a 10 minutes break. Yeah, and then we will talk about FPGA. Yeah. Okay, so any question? Yeah. So lab 3, if you complete, yeah, then you can fully understand today's lecture. Yeah. Okay, good. 10 minutes.